Okay, so we're working on Recitation 2, problem number 6. Okay, so problem number 6, we're actually told, I'm changing this slightly around. So imagine that we have, so ultimately, right, so we have some material, and there's some layer of material called N2. Actually, I really wanted to make it bigger because I want to make sure you understand this idea and teaches you a little bit about construction of new ideas in physics. So that simple problem, right, is actually a beautiful idea and extending your ideas in physics and where we get these intuitions and ideas and stuff. So we have a layer of material. We're told, right, N1 happens to be air. We'll just call it N1. Okay, so N1, and we're told that the angle of incidence is theta 1. And once it hits a material called N2, it's a sandwich material, so a parallel layer, then we hit another layer called N3. So basically we have a layer of material. In the example, right, we're told that this is, for example, ice. We're told this is the index of ice, and this is water, and we'd like to know exactly what happens, right, after it reflects into the ice. So well, actually, let me put it in. So this is 1.0. I'll have to look up N2 for ice, but let's call it ice. And this is water. And so the question is, what is the angle that comes out over here? So we know this light ray, because the ice, right, is higher incidence fraction, we're expecting an angle like this deeper into the material. And I don't know what the index of water and fractions are, so I can't tell you exactly, but let's do it mathematically and make sure it's a beautiful idea. So we have that Snell's law in the first interface, right, says that N1 sine of theta 1 is equal to N2 sine of theta 2. So here is theta 1, here is theta 2, this angle. Okay, so we're going to do another normal. And I know it's terrible, right? My handwriting is terrible, my graphs are terrible. And so this angle, right, these two lines, so this light ray comes straight down and then hits the next interface, which is second layer, right? And that is, so this angle here, right, because we know parallel light rays having a diagonal light ray, this must be the same angle, theta 2. And actually, I really should redo this because I really don't want you to not miss this idea. It's a beautiful idea, and we can actually create conservation principles behind it. So here's theta 1, and not drawn properly, so let's bend this way. It doesn't look like it's bent, but let's assume that this is, so it should be a bent light ray, but my light ray is going to be off because I really want you to understand this. So here's our normal again. So N2, so we know the first equation says that N2, which is the water, the ice above the air, and so we're expecting a parallel, so we don't know what the height is, but we're not told, it doesn't really matter. We know that N1 is equal to sine theta 1, N2 sine theta 2. But what's really key about this is that if these two surfaces, right, are parallel to each other, which ice should be, right, so the bottom layer of the ice and the top layer, they should be about the same distance, right? We expect that since this perpendicular and this perpendicular are parallel to each other, this angles must be exactly the same, theta 2. But I also know that if this is theta 2, I can use the second angle and say this is N2 sine of theta 2, which is this angle, must be equal to N3 sine of 33. And this is kind of really cool because what you're saying really, right, is that we have some kind of a constant. N1 sine theta 1 is equal to N2 sine of theta 2, which is equal to N3 sine of theta 3. So whatever happened, right, is that we seem to have a conservation. Something index times the angle theta 1 is constant and it's conserved as the light ray travels between the materials. In fact, if I had a fourth material, and this is N4, you'll see that the angle, right, here, right, that comes out, theta 4, is equal to this. So we have a conservation principle that says that the light ray, as it traverses parallel layers of material, the equation n1 sine theta 1 equals n2 sine theta 2, n3 sine theta 3, and n4 equals sine theta 4 is conserved. So we have a conservation principle coming out from this equation. So this equation is leading us into some kind of a conservation principle that says when light rays travels from one material to another, this constant of n1 times the index of the material times the angle of the incident angle, right, coming in, right, is conserved. It's like some kind of a constant based, it is constant based on, well, the angle theta and the index of the material, but whatever it is, it's conserved. In fact, I can say it another way. Light's coming in here, right? It's as if this material N2 didn't even exist, because the N1 sine theta 1 is equal to N2 sine theta 3, N3 sine theta 3. So they're equal to each other. It's as if the ice didn't really matter. Light comes in and it bends into the material, whether it's water or ice, air, from air to water, the same angle will occur. So even if you put a layer of ice, and that's what you expect, right? Because when you look out the window, right, we don't expect things to bend slightly. We always expect that when I look at something, it might be shifted slightly, but the angles don't change. When I look at objects outside a window, in the distance, I look at objects, and when I push the window up, right, I see the object, and when I pull it down, maybe slightly shifted because the thickness of most windows are maybe less than a centimeter, right, or maybe 5 millimeters thick. And so you'd actually see everything shifted by 5 millimeters at most. But so this is kind of a beautiful idea. So in this case, right, if somebody gave you, I don't really need to know the index of ice to tell you the exit angle of water. So basically, all I have to know is that n1 sine of theta 1 is equal to n3 sine of theta 3. This only works so long as these surfaces, right, are parallel to each other. So in this case, we have, let's make up some numbers. I'll select 30 degrees, and so we'll calculate theta 3. So, and water has an index refraction of 1.33. We did this a couple of times already. So this would be 1.0 times sine of 30 degrees is equal to 1.333 times sine of theta 3. And actually, I shouldn't have done it this way. Actually, it's preferable, right, that you play with the equation and say that sine of theta 3 is equal to n1 sine of theta 1 divisible by n3, and then do a substitution, say that theta 3 is equal to arc sine of n1 sine of theta 1 divisible by n3. So this would be arc sine, and the last step, and I actually didn't do it here, so I should have been doing the equations, because you tend to make mistakes. You substitute it too early, and I substituted too early, and I should have been really reinforcing the idea that you play with an equation instead. So theta 3 is equal to n1, which is 1.0 times sine of 30 degrees divisible by the index of material, which is 1.33, and I won't actually calculate the answer, they're just numbers. So it's 1.0 times sine of 30 degrees is half, so it's 1/2 divisible by 0.333, and take the inverse sine as theta 3. Okay, so the main idea you should get out of this, right, is it's as if the bending, right, didn't really matter in the material. This ice thickness, right, does cause this light ray to be slightly displaced further, but they're parallel. So, but there would be a displacement, but this is unaffected by, basically, the angle of coming out is unaffected by the thickness of the layer of ice. It's as if the ice didn't really exist. So the bending angle doesn't really matter. So this point, right, would actually get shifted, right, because the thickness, as the thickness gets longer, this point compared to this point gets a little bit further. So we can actually calculate this and say, okay, well, if the thickness is h, and the ratio of this displacement d over h is equal to tangent of theta 2, we can actually do those calculations. That does change. D does change based on the thickness of the ice, the h. And that we do expect. But the angle theta 3, right, it's immaterial of this material. So if you have 7 layers of materials and they're asked what is the exit angle, don't calculate all these. Just know that n1 sine theta 1 is equal to n2 sine theta 2, which is equal to n3 sine theta 3, and go all the way to the end and just say, so the ultimate angle theta 3 is the exit angle, would be just basically Snell's law as if the material did not exist. So that's the main idea that you get out of this, okay? So it's kind of an idea. So remember, it's kind of being conserved, right? Something is being conserved with this light ray, this quantity called n1 sine theta 1. And that might lead into an idea. We're constructing new ideas in physics, even though we're actually taking this one equation across. Anyway, so that should be problem number, last problem in homework number 2, or recitation number 2.